Do you guys watch The Office?
Yes, I do.
You do? Okay, sweet. Here we go.
So hello guys, welcome back to the video. This is Rituraj and Wire, and today we are going to do Lenz Law. So what is Lenz Law? You might know that Lenz Law is a rule that explains that we need to oppose the induced current that is being generated in the circuit. But actually, to understand Lenz Law practically, you need to understand why does it oppose the induced current. So basically, the whole concept of Lenz law is nothing but a practical concept of conservation of energy. The nature resists any changes. We can talk about any subject like physics, chemistry, mathematics. In everything, not mathematics, in everything, nature resists changes practically. Okay, and this is what we call the conservation of energy. Everything that is being created needs to be destroyed or needs to be conserved. Okay, that is what we say about the conservation of energy. So let's begin with the Lenz law. I'm going to explain you this today, and after completing this video, all the different types of concept about Lenz law and what it revolves around, it's gonna be so crystal clear to you. So yeah, let's begin with the video. First topic. So when we studied Lenz law the first time, as I said we understood it as an induced current opposes change in flux. But to truly master it, if you need to understand why nature does this, as I said, and the answer is breathtaking. Nature opposes changes because if it didn't, energy would be created from nothing. And we can't afford an energy that is being created from nothing and doesn't get destroyed or conserved. So imagine a magnet approaching a coil if the induced current helped the magnet instead of opposing it. So we are talking about a case here that when a magnet opposes an coil, so as we know about Lenz law, so Lenz law, what does the Lenz law explains? That if a magnet goes towards a induced current, the induced current will oppose the magnet to not move towards it. But what happens if the induced current just supports it? It makes it comes toward it. So what would happen? The magnet would accelerate, more flux changes, more current, more help, and magnet accelerates more and infinite speed from nothing. Okay, if the magnet is too big and the induced current is also we can say on a large scale and there is a much distance between them, the magnet could gain an infinite amount of energy and acceleration. Okay, so this violates the conservation of energy that we might have learned in class 9 and 10th. Okay. So the nature must oppose. So Lenz law is not a rule someone invented. It is a logical necessity of energy conservation. So this is the base about what Lenz law is actually. Okay. So to solve any Lenz law question, we just need 3 steps to follow. Okay. Following these 3 steps can solve any type of Lenz law question. So the first step that we need to do is know what is happening to the flux. Is the flux increasing, decreasing, or changing? And why it is decreasing, increasing? What is the purpose or why it is doing that? So it might be due to the magnet is moving towards it or away from it, current changing, or the coil rotating. The step 2 is what is actually happening to the flux. Is it increasing? Is it decreasing? If it is increasing, then there would be a opposing current that would stop it from increasing. And if it decreasing, there would be an supporting magnetic field that would help it to increase. Okay, so to find the direction of the induced current or the magnetic field, we can just use the right hand thumb rule that states us that for current we can just use our thumb that would define the direction of the current or the induced current, and the rest of the finger that is being curled around it would define as the direction of the magnetic field. So it is simple like that. We can solve any Lenz law question with just 3 steps following this. Okay. Now we will talk about some different types of cases on Lenz law. So the first case we are talking about is the magnet and the coil, or we can say the first example that we took as a practical example to define Lenz law. So what would happen if we took a bar magnet and use it north pole to just move towards we can see a coil or a wire, so that has a charge being flowing from it. So the flux from the coil would increase from leftward, means the north pole is coming from left, so the coil would increase its field from leftward only, and induced current must oppose, so create rightward field inside coil to oppose it. So right hand thumb, what does the right hand thumb rule shows? So the current flows clockwise when viewed from left. So if the current is flowing from we can say from the left side, so from the left side, the field would flow like this. Okay, so the clockwise signal. So left face of the coil becomes the north pole. It repels the approaching magnet, and you must apply force to push the magnet. So the external force that we are applying to the magnet to just to oppose the repelness of the coil is what we call the electrical energy generated. Okay, the energy we are providing is just being converted into electrical energy in the coil. Okay, so what happens when the north pole recede from the coil means it is going away from the left side. So the flux is decreasing now. So the induced current supports, does not let the flux decrease. So it supports creating a leftward field, and left face becomes the south pole, attracts the receding magnet, and again you must apply force. That is what we call the electrical energy. So in both the cases we are generating an electrical energy, and the coil is trying to maintain that the flux does not decrease or increase, means that it is not allowing the change in the flux. So the pattern is the coil always create a phase that fights what the magnet is doing. So approaching, repel, receding, attract. Simple as that. Okay. In the second case, we are talking about two coils that we are naming as primary and secondary. So what happens if we place two coils both we can see a close distance between them. So what would happen? The primary coil would, if we increase the current in the primary coil, then it would increase the flux through the secondary coil. So to oppose the change in the flux, the secondary coil would induce a current to stop the flux, or we can say to decrease the flux. So the secondary current flows to create an opposing field. So the field from the primary coil that is being made because of the increasing current from the primary coil is being now cancelled from the secondary coil opposing field. So it acts like cancelling the primary growing field. So primary current decreasing, secondary current, now the case reverse. When the primary current decrease, means the opposing means the field through the primary current also is primary coil is also decreasing. So the secondary current flows to support the collapsing field. So this is what we call the mutual inductance. In this case, why do we call this as mutual? Mutual means helping each other out. So they are helping each other out to being in a balanced phase, not changing the flux inside them. Okay, now the case 3, coil rotates in magnetic field. So what would happen if we rotate the coil in a magnetic field? This is a very important concept because this directly connects with the AC generator concept. So what would happen here is that a coil is rotating in an electric field, being from perpendicular to the parallel to the field. So what happens? Flux decreases from maximum to 0. So when it is at perpendicular, it is being 0, and when it is at parallel, it is being at maximum. So induced EMF is maximum when flux is changing fastest. When coil is parallel to the field, it is being maximum, and induced current tries to maintain the decreasing flux. So yeah, that was case 2 and case 3. Next case we are going to do is jumping ring experiment. So basically it is a very awesome experiment. You can watch its practical video on YouTube too. So what happens here is that we are placing an conducting ring, or we can say a material that is being a conductor material ring in the solenoid. So what would the solenoid do? It makes everything, we can say, a temporary magnet, a conducting material magnet. So what would happen here is that the change in the magnetic flux induced in the current in the ring, so it would oppose the Lenz law would oppose the change in the flux in the ring. So what would happen is that by Lenz law, induced current opposes, so ring repels from the solenoid and ring jumps up. So it would move like it would strike the solenoid, and just, we can say, it does not strike the solenoid, it just tries to escape the solenoid. So when ring is held above the solenoid coil, it levitates. This is what we call the maglev principle. So this was the last case. And I think these 4 cases are, we can say, the deepest we can go into the Lenz law to understand its concept practically. Okay, we're gonna derive the energy conservation formula for Lenz law. So work done against the opposing force is equal to the electrical energy generated and is equals to the heat in the resistance if a rod moves with velocity v in field v. So before going on to the example and deriving the formula, I hope you now understand what we are talking here about. So like I was explaining you about how when the magnet moves towards the conducting coil, it would feel the repelness from the coil. Okay, because according to the Lenz law, it cannot change the flux. To help the flux to reduce, the induced current from the coil opposes the movement of the magnet by becoming the south pole. The north pole. So to move the magnet towards the coil, we need to apply an outward force to it. So what would happen to that energy that we are applying, or we can see the outward energy? It would convert into electrical energy that we are talking about here. Okay, so the opposing force, we can call it as B equals to B into I into L. So what is B? B is the magnetic field, I is in the current. So work done per second is equals to B into I into V is equals to power input mechanical, and electrical power is equals to E into I equals to BI VL. So these are equal, energy is conserved, not created. So this proves that energy is conserved and it is not created. So basically, we just proved the energy conservation principle in the Lenz law. Why does it work? What is the concept behind it? Okay. We are in the last part of our video, so I'm gonna talk about some of the traps that are being used in the examination question that might confuse you in the Lenz law topic. So to be prepared for that, I will teach you about 3 traps that you need to identify and close them. So first trap is Lenz law only applies to magnet and coil. No, it applies to everything. The eddy current in the metal plates, the back EMF in the motor, the self-induction inductors, all are Lenz law. Okay, the second trap is confusing the phase polarity rule. So current anti-clockwise, when viewed, that phase is north pole, and when the current is clockwise, that means the phase is south pole. So in AC generated, maximum flux is equals to 0 EMF. This is wrong, because in actually when the flux is 0, then the EMF is maximum, and when the flux is maximum, the EMF is 0. That is the actual case. If you know about we can say the force or the actual AC generator working principle. So students think maximum flux means maximum EMF. No, EMF is the rate of change of flux, not flux itself. When flux is maximum, it is momentarily not changing. EMF is equals to 0. When flux is 0, it is changing fastest, means the EMF is equals to maximum. Okay. So guys, this is the summary and the formula of the video that you can use to practice and revise the concept again. So the Lenz law, induced current opposes changes in the flux. That is the main principle around it. Mathematical formula, negative sign in E equals to minus N d phi by dt is because of Lenz law. Okay. Physical basis, conservation of energy. I told you the core concept of Lenz law is conservation of energy. Direction rule, right hand thumb rule, we can identify the induced current or the EMF in the, or we can say the electrical field in any coil through right hand thumb rule. Phase polarity, anti-clockwise is north and clockwise is south. Okay. Flux increasing, creating opposite field. Flux decreasing, creating supporting field. Magnet approaching, near phase is equals to same pole. That means it is rippling. Magnet receding, near phase, opposite pole. The coil would now attract. So metal plates in changing B, eddy current opposed changes, and coil rotating, EMF 0 at maximum flux, maximum at 0 flux. Okay. So yeah, that was all the summary, and I will also show you a diagram that what we are talking about in the video. So N pole formed repel means watch here. Approaching means the north pole is being approaching as the bar magnet towards the coil. What would happen? The current is moving clockwise from the exterior, so flux would increase leftward. So you push magnet, do work, electrical energy converts heat into the coil, and energy is created is equals to 0. Means whatever the energy you are pushing into the coil, it is being formed into electrical energy, and that electrical energy is being released as heat. So whatever the energy you are providing is going out as heat, means nothing is created, nothing is being destroyed. So the energy remains the same. So Lenz law, magnet approaching coil and pole formed on near phase to repel. So this is the diagram about that. So hope you all understand this topic very well. If you have if you have any doubts, you can comment me out on the video, or you can just watch back the video. Yeah, I would meet you in the next video. Bye.
And now, folks, it's time to say goodnight. We sincerely appreciate your patronage and hope we've succeeded in bringing you an enjoyable evening of entertainment. Please drive home carefully and come back again soon. Good night.